Hello, my name is Maria from mathmammoth.com. In this lesson, we're going to look at similar figures. And you probably already know that similar figures are those where the figure retains its basic shape, but not necessarily its size. We can also use geometric transformations to define similar figures. We call two figures similar if there's a sequence of transformations that maps one figure to the other, using translations, rotations, reflections, and/or dilations. For example, this crab here, if I just move a copy of it, then these two are definitely similar figures. In fact, they are even congruent figures. But the same is also true if, say, I rotate this one and then also dilate it, shrink it proportionally. These two crabs are similar figures, and I could still flip it or reflect, move it somewhere else, do more transformations, and they are still similar figures. The same is true of the pentagon. Let's say that I dilate it or enlarge it proportionally. I move it, I flip it, rotate it. There we go. These two pentagons are similar. But if I were to shrink it non-proportionally, then we get a figure that is not similar to the original. It does not retain its shape. Here we have two triangles, and our task is to prove that they are similar triangles, or check whether they indeed are similar triangles or not. And the way we can do that is to use geometric transformations. If we can find the exact geometric transformations, or sequence of them, that maps one triangle to the other, then we have proven that they are similar. So we're looking at this purple one, and how would we transform it so it becomes this blue triangle? Let's say that I first of all rotate this triangle 90 degrees clockwise. All right, looking much better. And let's say, okay, I could either dilate it and then move it, or move it and dilate it. You can do these things in many different ways, many different orders, but let's say that I move it this certain distance over here. And now I dilate it from this center point here, dilation center point over here, but I use this corner to do so. I am able to dilate it so it matches exactly this other triangle. So yes, there was a sequence of transformations that mapped the first one to the other, so they are indeed similar figures. Here we see a set of coordinates. There's a shape, a triangle, and there are two transformations that are done to it. And we are given the coordinates of the vertices of the triangle for each transformation. What are the transformations? Let's look at those coordinates first of all, and not do anything with the grid yet. The original figure has points P, Q, R, so the first one is -5, -2, and it becomes -5, 2. And this point, 0, -5, becomes 0, 5. And this point, -4, -5, becomes -4, 5. Can you see what changes and what doesn't? Can you tell what transformation it is? You notice that the x-coordinate does not change for any of these points, whereas the y-coordinate becomes its opposite. What transformation was that? You remember? If you don't remember, you can think through it. Because let's say that you have a point somewhere, and then if it moves so that its x-coordinate does not change, it is somewhere here, but the y-coordinate becomes its opposite, then this is a reflection in the x-axis. So the first transformation is a reflection in the x-axis. And what about the next one? If you compare these coordinates and these here. Point P prime changes so that -5 becomes -2.5 and 2 becomes 1. And here 0 does not change, 5 becomes 2.5. And here -4, -2, 5 and 2.5. The coordinates were halved. So what transformation is that? You probably remember, that's a dilation from the origin. The center point of the dilation is in the origin. Okay, so we have solved the problem, but let's double check our answer by actually doing these transformations to the triangle. If we reflect this in the x-axis, and there it is. Do the coordinates now match here? We have negative 5, 2, yes, 0, 5, and then negative 4, 5, yes. And then the dilation from the origin, so I will move the reference point, make the center of the dilation here, dilate it, exactly 50%. And let's check the coordinates now. We have 0 and 2.5. Yes, that's Q prime prime. We have negative 2.5 and 1. Yes. And then negative 2 and 2.5. Exactly. So that worked. And these two triangles are similar triangles. They have the same basic shape. One just has been transformed according to these geometric transformations. Okay, well done with this lesson.